Welcome everybody to this new installment of the DinAmicI seminar, seminar. Today we are very happy to have one of our own, Tanja Schindler from Scuola Normale Superiore in Pisa, will tell us about almost sure asymptotic behavior of Birkhoff sums for infinite measure preserving dynamical systems. A very interesting topic, by the way. Okay. Thank you very much, Tanja. Here's to you.
Okay, well, first of all, I would thank the organizer for giving me the opportunity to speak here. And well, we have a long program, but I will keep everything short. So I will first give a short introduction, what we are actually interested in and why we are interested in that. And then we will basically look at two classes of functions over an infinite measure system, namely those which are integrable and those which are not integrable. And finally, I will give an outlook where one could further think of. Okay, so, okay, I have to use this one. Let's just introduce a little bit of the setting. So we look at conservative ergodic measure preserving transformation on a sigma-finite measure space, however this looks like for the moment. And for simplicity, we only look on observables which are non-negative because the theorems are not so easily to generalize to all systems, but it's it shouldn't make us worry for the moment. And well, we will look at the Birkhoff sums, which well, I guess everybody of you has seen the Birkhoff sums before. So the observable, the sum of the observable composed with the chase iterate of t. And now we ask ourselves, can we see anything about the pointwise convergence of the Birkhoff sum? And yes, of course, if we look at the probability measure space and also assume that f, our observable, is integrable, then we obtain by Birkhoff's ergodic theorem, which everybody of you know, I guess, that the Birkhoff sum divided by n converges almost surely to the integral over f d mu. So, but now let's assume we are no longer in a finite measure space, but we go now to an infinite measure space. Okay, so and then if we still assume that f is an integrable observable, we get by, well, very classical theorem by John Aaronson that we either infinitely often underestimate the sum by some norming sequence Bn. We can choose any norming sequence Bn of the norm, so we either infinitely often underestimate it or we infinitely often overestimated made the sum by this norming sequence. So in any case, we don't get immediately an analog of Birkhoff's ergodic theorem for that case. But maybe we get something else. So we also know that we have Hopf's ratio ergodic theorem. So if we add another function, which is also in L1, then, well, it basically boils down that that we start with both sums from the same x, and then we get some almost sure convergence of the fraction of those of the both Birkhoff sums. But well, we would also have something more. But first, let's look at the case that f is not in L1, and then, well, we can have a very, very easy example. So we could just say that f is constant, almost surely. And then we also get some almost sure convergence. Well, it's of course the trivial case. And Marco and Normale have given some conditions when such a convergence also hold without f being like a completely trivial example, like f being constant. Okay, so far the things we know. And now I will introduce the two questions we are interested in. And well, the first is we are going back to f being integrable. And in this case, we are looking for something, okay, we know we can't look at the sum by itself divided by a norming sequence. There we don't get a strong law of large numbers, but can we truncate it a little bit? And of course, we want to truncate as little as possible to get convergence like this. And this will be our first question. And the second question is, okay, now we look on f not being integrable. And then, well, we have seen that it's possible and to get an almost sure convergence, but well, we just want to give some more conditions to look at that. Okay, and now, well, we go to the first question, and we also ask ourselves what we can expect from a finite measure case. So I will just compare this situation with a situation that we are in an infinite ergodic theory. So we look on a probability measure space and also an observable, which is non-negative for simplicity. And okay, I forgot to state, okay, that where we have also our T is again ergodic and measure preserving, but then we are in basically in the same situation as we have been in an infinite measure case and the integrable observable, namely that with any norming sequence Dn, however we small or large we choose it, we either almost surely infinitely often underestimate the sum as this norming sequence, or we infinitely often overestimate the sum with this norming sequence. So also here we can't get a strong law of large numbers, or well, an equivalent to a Birkhoff's ergodic theorem. However, what we can get is convergence in probability, and I just well, if you just look at in the special case of continued fractions, you can look at the book by Chin, or otherwise also in Aaronson's book, there are quite concise the conditions for convergence in probability. And what you can also get is you can truncate your sum in nice way, with which means you look on this on your sum and then delete the maximal term of this sum. So you just look at the first n observations and then delete the maximal one. And then you can get a strong law of like this. I also have to add, I just wrote here under suitable conditions. So these suitable conditions are sometimes quite strong. So you need some mixing conditions on the system and also some conditions on the distribution function. But then, well, at least in certain situations in which H is not integrable, you get this convergence, and well, you get this more or less concisely done by Aaronson and Nakata. And well, also if you are particularly interested in continued fractions. I think this paper was the first paper considering convergence under trimming. Trimming means like that you delete these maximal terms, or here just the first, the largest maximal term for dynamical systems. Okay, so but now can we get a similar statement in the infinite measure case? And for the first thing, yes, so we can get convergence in probability under, again, I don't want to say precisely, but under nice conditions on the system, you get convergence in probability. And now, well, can we also get something like this trimmed case? And well, if you think a little bit about it, it becomes quite obvious that if you just trim the largest entry of your Birkhoff sum, this is not doing very much because since your observable is integrable, even this largest entry will not be so large in the infinite measure case. But we can do something else. And that's now our first theorem. Okay, and well, to state this, I apologize, I beg you for a little bit of patience to get through some notations, but it won't be too heavy, and then I can state the theorem. To start with the notation, we first introduce the first return time. So this is we use some set which is known, so it has measure 1, and define the first return time as the minimum of those iterates such that tk enters E again. And well, we also should notice that the first return time is almost surely finite. And then we can, since this is the case, it makes sense to induce the induced map, which means it's a map from E to itself, and it just goes this orbit until it enters E again. And so we have a map which is a measure preserving and ergodic on this reduced space, the space reduced to E. And then we define the level sets. Those are all these sets such that this return time equals n with respect to this to a measurable partition on E. And we define the super level sets, so we can just take them as a union of these sets AK, but we could also think of, well, those are all these sets which after time n have not returned to E. Okay, I guess most of you have seen similar notations before anyway, so we can continue. And this, I guess, is a new notation. So we define the longest accursion out of E beginning in the first n steps. So this means we look at the first n steps, and then we look at the excursion. This the map T does before entering E. So this might be like that. There are a lot of short excursions, and like 2 digits before n, at like say at n minus 2, a very, very long excursion starts, and it might only enter E again at, let's say, 2n. So this would be like our latest excursion. It's not so important what the excursion which is happening inside the first n steps, but the excursion which starts within the first n steps and then might when it comes back to E. Just to clarify this, because I think it's not a completely standard notation to look at. And then we look at the number of visits until to the set E up to the time n, which for the following of this talk we will denote by En. And then we have that we can write this quantity m as the maximum of the Birkhoff iterates of phi composed to Te to power k, if we go from 1 to En. Okay, and so I think now we have defined all the notation we need. So we, no, I think we need another thing, a mixing condition. And this is the definition of Psi mixing. So if we consider some random variables on a probability field, and those, and we see that we look at the sequence of a subset of random variables from H to K, and the sigma algebra generated by these random variables we define by FHK. Then we can define the a notion of Psi mixing as the primum of all fractions like this. So we look at the set which is generated in the first in the sigma algebra of the first J random variables, and another set which is in the next J plus n is generated by J plus n and to infinity of the random variables, and then we look at this quantity, and this and if this quantity goes to 0 for n going to infinity, this sequence is called Psi mixing. So if you haven't seen anything like that before, think of it as the random variables becoming more and more independent the further away they are from each other. But it's actually quite a standard condition in a dynamic system. So if you look for more properties, you can look at the survey paper from Bradley. And well, there are a lot of piecewise expanding interval maps. And if the observable are constant on the cylinder sets, then you get this Psi mixing property. And if you look for a concrete example, then you could, for example, look at the continued fraction expansion. So the entries of the continued fractions are actually exponentially fast Psi mixing. Okay, but now we have all the conditions for the theorem to state, and so that's now doing. So I didn't want to state all the conditions again, but well, just let's consider an infinite measure space and T Ergodic, measure preserving and conservative, and well, this set E with a normed measure 1. Okay, just the standard system. And then we assume first a property on the mixing property on the return time. So we assume that the iterates of the return times are Psi mixing and also with a certain speed. So the sum of Psi of n over n is finite. And as a next thing, we look at the super level sets. And the super level sets of the induced transformation have to fulfill a certain property, which, well, it doesn't look very easy to understand right now, but you could think of something as log n over n. And okay. And then if we just need those two conditions on the return time, and then we get that no matter which f we choose, if it's L1, we get exactly what we wanted. So we have a sum which we truncate a little bit. So we don't look at the sum up to n, but we look at the sum up to n plus m of n, e, and x. So this, just to remember, m was this excursion, which the longest excursion which started up to the time n. So we might we will add up something, and this might be large or might also be small compared to n. And so we have like this truncated sum which we were looking before, and divide it by a norming sequence alpha of n. Alpha of n given here, it can be computed just by using the super level sets, and then we get a convergence. And this alpha of n also does not depend on f. We just get the integral over f on the right hand side. And well, just some comments still about this theorem. So this norming sequence alpha of n also coincides with the weak law of large numbers. So, well, this was a little bit of assuring for us, because this means we haven't truncated our sum too strong, that we just like do something completely. It's still similar to the original sum. And these conditions 1 and 2, which we had in our theorem, they are basically necessary conditions that that for the induced system we get a trimmed strong law. And yes, as said before, this condition 2, which was a little bit difficult to see what to do with at the first spot, was something like, if you look at the super level set, they can behave like something like logarithm to the k of n over n, and then it would be fulfilled. And well, as a second, then now we will state the theorem, which is similar to the first one and somehow related. But well, I'm sorry, we still have to do a little bit of notation before doing so. So we define the longest accretion out of E seen up to time n. So now what we do is we go up to n and look on the longest time n the iterates were out of E. This might be like, okay, you go somewhere, then you do something and enter E again, but it might also be that it's at the last point. So you are like at n minus k, you do k steps, and then you are at n. But this does not mean you have reached E again. But it might be like that this last excursion still is already the longest, and then this would count into W. Okay, and with this we have a related theorem. So, well, this is not completely what we were asking in our question. In our question, we were asking about a somehow truncated sum. Here we don't truncate the sum, but we truncate the denominator. So we don't have a constant by which we divide, but something which still depends on x. So we are, in spirit, we are like closer to Hopf's ratio ergodic theorem. I say that we divide by something which also depends on the starting point x. Okay, and well, I just talked a lot, so you might think, okay, but for what is this? Is there actually some example we can look at? And well, there are actually a lot of examples, but we'll just give a very easy one. So just something I guess you know very well. So we look at interval map from 0, 1 into itself with a partition and just into 2 pieces, and such that T is piecewise monotonic and twice differentiable, and both the slopes map into the complete interval 0, 1. And away from 0, T is uniformly expanding, and we assume that we have some slowly varying function such that close to x, close to 0, our transformation T of x behaves like this. And this slowly varying function also has to fulfill some property, so you can't just take any slowly varying function, but one which doesn't vary too rapidly, spirit-wise. And so if you take
May I interrupt you for a second?
Sure.
I'm lost as to what x0 is.
X0 should be a 0, sorry.
0, okay.
0, sorry.
Okay,
yeah, that was a stupid copy and paste mistake. No. If you copy something from somewhere else.
Absolutely
but
fine.
Sorry, x0 equals 0.
Okay.
Thanks for interrupting me. This was a good question.
Well, okay.
So you just have one indifferent fixed point which is at x0 equals 0, and then close to this point, this T behaves like this. And well, this, if you just think of L being a constant, then this would be the case for the Fari map, or the if you take the Pomo Manville and the Duerani Sassol Vienti maps, they have a parameter, and if you take this parameter P equals 1, then we would just be in this case. So it's not that we consider something which is completely weird and out of the reach of something. So, but now I will give a short sketch of the proof, how to do things like that. And so I just wanted to show you again shortly the theorem, because where we were already looking at another theorem and I was talking a lot, and so one can easily forget what was actually the theorem. So we have the interesting part was, okay, there were some conditions, and we have a sum which sums up to n plus this excursion time, but then we divide by a sequence of real numbers which don't depend on x anymore. Okay, so first I should say we just proved the theorem for x being in this set E, because then as it's conservative and ergodic, we can easily or immediately transfer it to the whole system. And then, well, also I beg again for stamina to introduce a little bit more of notations. So we remember that R with E and only with E and N were the first, the number of visits to the set E within the time N. And now we don't look only until the time N, but to the time N plus M. And then, well, we also remember this set M, which is the first, the longest excursion starting up to the time N. And then we define the return time to E as we defined it time E of the nth return to E. So if you want to have the nth return, you have to sum up the first return time and the second, and so on. So you get this sum. And we also, what we will need soon is its trimmed version. So we look at the tau of n, and then we subtract the maximum of the return times. Well, this at the moment it does not have like intuitive meaning. It's more that we need it for technical reasons. Okay, I guess now you had long enough look on the notations, and I can start the proof. So the first step is like we look at the sum we had before. And for the first one, we don't divide it by a sequence of constants, but by this return time up to n plus m. Okay, so obviously at the next point we and well, of course, this thing, if you look closer at it, this thing can be proven by Hopf's ratio ergodic theorem. But now we have to do something with this denominator to make this converge somehow to a sequence of constants. Sorry. And so what we can see is we look at the nth return time and the trimmed version of the nth return time, and find out that this thing behaves somehow close to n. So it's larger than n and smaller to n plus the second maximum of those return times. So, and I can tell you this second maximum actually is small. We will just see in a second. And on the other hand, this trimmed version of the return time also behaves nicely in the way that we can find the norming sequence, which is such that the fraction converges to 1 almost surely. And this norming sequence is actually the inverse function of our alpha of n, the norming sequence we want to have later. And as a first step, using 2 and 3, we can finally prove that our return time to n divided by alpha of n converges to 1 almost surely. And now, well, it's just immediate. You have to put 1 and 4 together, and this gives you the statement of the theorem. Okay, I hope I did not lose you. but in case I did, and you felt, okay, you did not know anymore where you were, when we were, this is now a new starting point. And well, if you, just in case you were lost, you have a chance to get in again. And so, well, again, we have to start with some notation for the statement of the second main theorem. And so just to get back, what will we expect? Right now, we were looking at the first question that f is integrable. And now we look at the second question that f is actually not integrable. And so let's look at the notation. So we've introduced the induced observable of f. So we remember phi was the return time, and so we just each time we just sum up all the iterates of f until x is entering E again. And well, the simplest version of some function f is that it is constant on the level sets an. Okay, and being constant of the level set A corresponds to, well, the heating time function, which well is of course related to the return function, but still it's not completely the same. So it's the first natural number k, including 0, such that tk of x is in E. And also this is defined and also almost surely finite on x. And then we set the level sets En of this heating time function. Which, they are, of course, related to the level sets An. Okay, and now if we have some f, we are actually in this situation that our E is constant on the level set A, then we can write this induced version of f as fe as a sum of these of some constants fk, and this, well, since they are constant, holds for all x in the level sets an. Okay, and now we can state the theorem. Well, we just are in the same situation as before. Well, just the standard setting that we have an infinite measure space, which is conservative, ergodic, and measure preserving, and E is a finite set on this space, and we have normed the measure so that mu of E equals 1. And now we assume that f is not integrable, which is basically the main assumption on this theorem. And furthermore, now we have first we have similar conditions to the theorem before. So we have exactly the same mixing condition on the return time function phi e. So again, the these iterates have to be Psi mixing, and also Psi mixing with a certain rate. And now we also have a condition on f. We remember in the last theorem we did not care how f looked like. It was just f had to be integrable. Here we actually have to look at f being somehow normed. And actually, well, if you don't assume f is constant on the level sets, you we at least assume that it's bounded by two functions which are constant on the level sets, and those the induced versions of those functions behave like n if you restrict them to the level sets a n. And if we have this, we also have a condition on the super level sets. This again is exactly the same as before. I also might say something here of my strange notation. I just use the same, in case you want to look it up, I use the same notation as in the preprint, and I only gave a special case. So there are actually some conditions missing. So that's explanation why I go from 2B to 2D. And we have an additional condition on the wandering rate. So it's a condition on the super level sets, so that they behave nicely in this way. So, for example, the logarithm or a square of the logarithm would do for the wandering rate. And in that case, we get this strong law of large numbers. So we just take the sum and divide by n and get convergence to 1 almost surely. Okay, I also want to say something where I said this, the theorem I just stated before was a special case. So we were just looking on this norming sequence being equal to n. We're actually able to generalize this for some cases, but well, the conditions are not so nice to look at. And I then decided it would be nicer to give you a nice overview and don't bore you too much with the details. But one can actually, there are actually cases where the norming sequence Bn equals n times a slowly varying function. And well, actually the slowly varying, you can't just use any slowly varying function, but there are certain conditions on it. But it's still more than only a constant. Like, for example, we had some examples for log n being then and this works. And then if we have something like that, then we just have again this condition that f has to be bounded between two functions, and these functions behave like a b of n. So now we also can look at functions which are not in L infinity. I mean, also already in this case where we have that they behave like n, actually the function f does not have to be an L infinity function. But well, here it becomes more obvious that we are not only looking at L infinity function. And well, now I will also give you a short sketch of the proof, but right, as there are a lot of details involved in this proof, it will be rather short, but it's basically the main idea. So we look at the induced transformation, and look at the Birkhoff sum of this the induced Birkhoff sum, and we go to REN. And this thing behaves like a sum function. It was actually the same function we had before, the inverse function of this norming sequence alpha we had before, plus this maximal term of the induced function. But now, well, we have to go the step back, that we are in the induced system, to go to the original system. And then we get a number of very not so nice terms. So we get again this as sequence D of R, and well, this term basically corresponds to this term. But now, since well, there are also some remainder terms which we have here, and well, the basic problem is to take care of all these remainder terms, that they behave nicely. On the other hand, we can do something with this norming sequence. So this norming sequence behaves like n minus w of n ex. We remember this w was something related to m, but it was the longest excursion seen up to time n. And now, basically, the last step, where I don't wanted to go into details, is like, okay, if we look at this sum, these remaining terms behave nicely. With nicely, I mean those two summands add up to something asymptotic to w. And with that, where you get this convergence. Okay, and well, I might also give a short outlook where one might or might not be able to improve the results. So can we weaken some of the conditions, which would always be very nice to do. First of all, this Psi Mixing Condition. The problem is, if we have seen in the proof, we were using these results of trimmed sums in a finite measure case. And those results actually use the Psi Mixing Conditions. So there are actually examples with in the finite measure case with the same distribution function, for which trimming with just like deleting the largest entry would work, but they are only phi ref mixing. I don't want to give the definition if you don't know it, but it's reasonably close to Psi mixing actually, but it's not quite Psi mixing, but you don't get this convergence of the trimmed sum for this random variable. So it might be difficult to get rid of this condition. So if we want to get rid of it, then we have to get deeper into the system. Then this, maybe at the beginning, strange looking conditions on the super level sets. Also, this is a condition that we can apply the strong law of large numbers under trimming. And well, this is also, it's just the same for IID random variables, which one uses for Psi mixing random variables. And it's at least for the IID random variables, it has been shown that it's also a necessary condition. What one can now easily do is, like, one can change this condition, and instead of the squares here, one can add exponent to the k. And then in the induced system, one gets something like, okay, one gets a strong law of large numbers after trimming the k largest entries. So one does not only delete the maximum, but one deletes the maximum and the second maximum maybe. And this would correspond to adding the case largest run length. Like we don't have only this M, but we would have M2 and M3, something like that. So I mean, it wouldn't be difficult to do, but it would be a very ugly theorem to state. And we really didn't see that it would very much improve the situation. But well, that would be an easy way to improve things. And now the range of observables in the non-L1 case. As we have seen, we only have something that the induced version behaves like the induced observable behaves like n times the slowly varying function. However, if you have seen the last slide of the proof, you have these remainder terms which sum up, and those might not be not sum up that nicely anymore and cancel out this function W we had seen before, and so I guess it's not really easy to improve it very much, to increase the range here very much. Maybe small things are possible, but you will certainly not be able to use like any not L1 function. What one could try to do is like, okay, one could use intermediate trimming in the induced system. So what I didn't define intermediate trimming, but we have done before is like we go to induced system and use the trimmed version of we trim the maximum. And what I've explained in this case, okay, we might delete more than one maximum, which might just make things ugly. But intermediate trimming means that you delete a number of summands which depend on n. So for the first n entries, you might delete log n many entries. And well, this would be a different approach how to generalize this. But then, of course, like a lot of things might be more complicated to do. And yeah, I think it's almost 5, so I can stop. And well, these are the references I used. And with that, I would thank everybody for their attention.
Thank you. Thank you very, very much, Tanja. It's a very interesting talk. Do we have any, well, let me just clap physically. We are getting less used to do it physically actually lately. Are there any questions or comments by the audience? Okay, let me start with one, since this is a topic that I very much like and enjoy. I'm afraid this might be a very silly question. It might actually prove that I haven't understood much of your talk, but in the first part, in the first theorems, you have this n, capital N, which is your index, and you have the lowercase m, which is the size of the longest excursion starting in the first n times, something like that, right?
I just go to my first.
Yeah, that was it.
Yeah, it might be.
Yes, this m. If you go back one slide.
Ah, okay, you want to see the m, sorry.
Yeah, what I want to know is what is the, I mean, what should they think of? I mean, first of all, you say trimming in your theorem too, but it seems to me that you're adding indexes in the sum rather than cutting them, if you see it.
Yeah.
But I guess I just want to know, what should they think of what the relation to be between m and n? I mean, is little m much larger than capital M, or same order or smaller in general? It seems to me you add more stuff. It seems like you add another excursion, so you finish up the excursion, something like that. But maybe
yes.
I'm wrong.
Well, the idea is basically you might have had a very long excursion, and in this excursion, not very much is happening, and this was basically missing on your sum. So if you go back to the induced version, and this corresponds, this one long excursion corresponds to the digit you trim. So
that's why you call it trimming, because it's not much is happening. So you're picking up, just a small amount of terms. I mean, of function, basically.
Sorry?
No, I mean, I was wondering why you call it trimming. Now it seems clearer to me, but I might be wrong. When you say, when you do the excursion, not much is happening. So the amount of, addends of terms in the sum that you pick up is little, because f is very low there. Is that what's happening?
Well, I want to say, like if you have a integrable function and you have a long excursion, then like compared to the length of this excursion, within this excursion, I mean, you don't sum up much, because otherwise the function couldn't be integrable. And what one can do now is like look on the induced version, and the induced version up to n plus m. And then what you do is basically in the induced version, you trim the largest part, which corresponds to this m. Your largest entry in the induced version is this one produced by this excursion you do with m.
Okay.
And this one you delete, and you get the convergence. And so to actually do this, you actually had to first, in the original system, you have to first add this m, and that you can later in the induced system delete this large entry.
Okay, and I see there's another question by Alessio. Let me just ask one tiny little thing. So, but then you normalize, by alpha n, and seems like it's n is the leading index rather than n plus m. That's why I'm a little confused.
Well, yeah, I mean, this is, I mean, maybe you think more of my second theorem, because maybe this is more intuitive. I just go back there.
Yeah, the second theorem is more intuitive, in fact, actually, the way it's stated.
Because, well, then, I mean, the theorems are actually very easily being transferable into each other. I mean, there was not so much to be done additionally.
Okay, so you see the theorem 2 and theorem 3 are pretty much the same. You translate them into one another. So it's a redefinition of a capital N. Yeah, well, I mean, it's not completely trivial, but I mean, I don't know. Maybe we needed another page or so to get from one theorem and to the other. And then maybe in thinking of that, this might be more intuitive, that you say, like, okay, well, this W, which is related to M, this is like this long excursion you have, and in this excursion nothing is happening, so you have to delete it from the denominator. But we also thought it would be really nice to have a statement where we have a denominator which doesn't depend on X, and we just have
sum which we truncate slightly.
Okay. I apologize to Alessio for taking up so much time. Alessio, you have a question, so please.
Yes, thank you. And thank you also, Tanja, for this interesting talk. So I have just a curiosity about the first theorem. So it's about the conditions, about a possible application, because we, by we I mean also Claudio, studied a system related to the triangle map, which is a slow version of the triangle map, which is, let's say, an extension in 2 dimensions of the Faraday map, which seems to satisfy at least there exists for sure a set on which the induced map is Psi mixing, because
we actually have this system in our preprint.
I would like to ask about the other conditions, because there is these 2 conditions, one about the Psi mixing rate and the other much more.
I mean, we looked at this thing, and like this thing is not the problem, but this thing might be. So we were not able to prove this. So if you have an idea that one can also prove that would be great, because then your system would fulfill everything.
Okay, so the first condition, did you prove all the first conditions? So also the condition about the Cn over n?
Yeah, this is fine.
Okay.
But I mean, this thing is like something like related to the, I mean, if this thing halts, then the wandering rate is slowly varying. And
so when we studied the system, we had problems with this measure of these super level sets. So I was wondering whether, so the problem is the second condition, actually.
Yes.
Okay, understood. Okay. But thank you.
So if you have any other ideas, I mean, it would be very nice for us to have another example where everything works through. But well, I wouldn't be sure of this condition.
Yeah. Okay. Thank you. It's just this.
Any more questions? No one. Then I would like to thank Tanja very much twice for a very nice talk. So let's give her a little virtual and physical round of applause. And I'll see you all in 2 weeks for the next seminar.